Okay, in the previous video, we talked about the different partial pressures associated with the atmospheric air. And we said oxygen had a partial pressure of 159, and I told you, okay, now pay attention to this because we're going to change up that value. And the same would also apply to the partial pressure of carbon dioxide. Those two values, oxygen and then the carbon dioxide, we are going to be changing with. We're not going to focus in on nitrogen in this case because that's going to be an inert thing. We're going to only look at the oxygen, partial pressures of oxygen and carbon dioxide. So the partial pressure of oxygen in the atmospheric air is 159 millimeters of mercury. But that is not the partial pressure of oxygen in the alveoli of your lungs. And it's also not going to be the partial pressure within the bloodstream and at cellular levels. So why is that not part of it? Well, when you are breathing in air, the air that you're breathing in, even though let's just stick with the oxygen, even though it's roughly 21% oxygen, when it enters your respiratory system, it is mixing in with the air that was already occupying that space. So that was the dead air, or the dead air, anatomic dead space, okay? So some of the oxygen that you're bringing in is mixing with that. The air that was already in there already has a higher level of carbon dioxide and a lower level of oxygen. So it's getting intermixed. So there's three different things that there's three different reasons why those partial pressures are different. One, air mixes in with the anatomical dead space air, just what I was mentioning. Oxygen and carbon dioxide are constantly being exchanged at the alveoli. So oxygen's always going to be entering the blood, carbon dioxide is going to be coming out. So those are always changing. So you're losing oxygen there and you're gaining carbon dioxide. And plus, the alveoli has a high water content, H2O. So if you were to look at the atmospheric air at sea level, 760 millimeters of mercury, and we have to, that's what everything's going to be adding up to. So if we increase the amount of carbon dioxide in that atmospheric air, can you see how that's going to then force the other gases to decrease their percentage? Because remember, the bottom line of this, it all still has to add up to 760 millimeters of mercury. So initially we had the partial pressure of oxygen at 159, carbon dioxide was 0.3, but let's say we increase the carbon dioxide, instead of 0.3, go up to 5%, the other gases have to compensate and then come back down if our total value still reaches 760 millimeters of mercury, which is what Dalton's law speaks of. So as you bring oxygen into your system, partial pressure, or let's say 21% oxygen, 20.9, you inhale it, it gets intermixed with other gases, you're constantly losing gas into the bloodstream, so it's being absorbed by the body. Plus, some of that gases are now being taken over by a high water content in the alveoli. That has to compensate for it. So the percentage of oxygen in the alveoli is not 20.9%, but 13.7%. So the let me get a pen here. So the percentage of oxygen equals 13.7%. Okay. In parentheses, I'm going to put 20.9. So atmospheric. Okay, so you can see how there's a difference there. The percentage of CO2 in the alveolus is not 0.4%, but it's actually 5.2%. And in the atmosphere, that was the, what did I say, 0.4? 0.4 atmospheric pressure, okay? Plus we have a high water content, okay? So now we have to we still have to make it 760 millimeters of mercury. So if we were to do the equation, 760 millimeters of mercury times 13.7%, this actually equals not 159, but 104 millimeters of mercury. Okay, previously the atmospheric partial pressure of oxygen was 159 millimeters of mercury. Now it's 104 within the alveoli. Okay, now these numbers, you have to know these numbers, okay, because this is going to be playing a significant role in how oxygen and carbon dioxide diffuse across the membrane. So this is oxygen. So CO2, we do 700, let me go backwards on this one, 760 millimeters of mercury times 5.2%, and then this actually equals 40 millimeters of mercury. And before, if you recall, this was 0.3%. This was 159 previously. Okay, so you can see a significant difference from this one to this one. Okay, and from this one to this one. So you can see how the difference comes off. Now, again, if you were to throw in nitrogen, as well as the water vapors and some other minor gases, that would all still have to equal 760. So the next set of equations we're going to do here is look at the partial pressures of oxygen and carbon dioxide at your systemic cellular level. Then we're going to look at the blood and put them all together. So hold on, let me just pause this. Okay, instead of doing the equations on how to calculate the partial pressures at the cellular level, I'll just give you the net pressure on it. So the partial pressure at the cellular level, the systemic cells, the partial pressure for oxygen is 40 millimeters of mercury. So let's do at systemic cells, your partial pressure of oxygen equals 40 millimeters of mercury, and your partial pressure of CO2 at the systemic cellular level, that's going to be 45 millimeters of mercury on this one. Okay, so we have the alveolus. We have a partial pressure of oxygen at 104. We have a partial pressure of CO2. What did I say? Was it 5.2? No, that was a percentage. 40 millimeters of mercury of the partial pressure of CO2 in the alveolus. So let me put this in a parentheses here. So the partial pressure alveoli, okay, the alveolus was 104, and for CO2 this was 40. Okay, so this is the alveolus on here. Okay, just so you can have a comparison. So once we get down on how the gases exchange, this is some of the information that you need to be aware of. All right, so let's now just also look at the partial pressures of those gases within the blood itself. Now, I can't give you a set value because the pressures for oxygen and carbon dioxide consistently change. So here's what I mean by that. So here we've got a blood vessel, okay? and we have a red blood cell in here, okay? Red blood cells carry a lot of oxygen, and what happens is as the blood leaves the heart, starts to get dispersed throughout the body, it is going through a number of other capillaries, and as it's moving through the capillaries, it's losing oxygen and picking up carbon dioxide. So as this is moving in this direction, you're constantly losing oxygen. So let me just put oxygen's always coming off, and let's do carbon dioxide is coming in. Okay, so at this point, so you can see, let's say at this point, we could have at the alveoli, okay, inside the lungs, it is going to be much higher. So let's just for argument's sake right now say, so we're in the alveoli. So let's say we start off at 104. But by the time we get to the furthest point away where most of the oxygen's gone, most of the carbon dioxide's come back in, now we're looking at the alveoli of being 40 millimeters of mercury, and CO2 at this end would be 45, whereas at the beginning would have been 40, okay? Because the reason why it's changing is we're constantly adding more and more CO2, and then we're constantly removing oxygen as it moves throughout the system. So I hope you understand the basic concepts. Now I think the next thing we are going to look at is, I think here's where we're going to start talking about the movement of oxygen and carbon dioxide across the membranes in the lung, and then we're going to get to the cellular level.